So we've talked a little bit about resistance, and mostly we've talked about the resistance of wires. In most of the time, the resistance of wire is a bad thing. It slows your computer down. It causes heating in the wires in your house, which does cause fires sometimes. Electrical fires are the leading cause of house fires in the United States. So we've talked about it mostly as a bad thing, but of course that heating can be a good thing, right? The toaster wire in your toaster, you want it to get hot so you can have toast instead of bread. But often within electrical devices, resistors can play a lot of different roles. And we're going to have to kind of ease into that to see, how they might be useful in other ways. But, sometimes, so not only do you have resistance of wires, sometimes you buy things, or there are components that are there just for their resistance, right? So here's a picture of the inside of some electrical device. Each one of these is a resistor, and it turns out that this color-coding banding, these colored bands, are a color code where you can actually read the resistance of them if you know the code. If you were to scratch off some of this ceramic outer insulating layer, then what you would see is this ribbon of wire. And we've learned that a wire that is thinner and longer has a higher resistance than a wire that is thicker and shorter. And so you see that a resistor that's been cut into this helical shape like this, where the bands are very thin, and there's many bands, would have a higher resistance than something like this, where it's cut into thicker bands. Here are some resistors that I just pulled out of my garage. Various shapes. This is kind of an older style. This is a newer style. Here's a tiny little one. The size of them has more to do with their ability to dissipate heat. In other words, how much power can I put through this, or how much current can I put through this without it breaking down, than it does to do with its actual value of resistance. This is a variable capacitor, and so if you've got a knob on a guitar amp, or really almost any device, and it turns smoothly, that knob is almost certainly a variable resistor. And so, this one is 250K, and so this is a resistor that can vary from 0 ohms to 250,000 ohms. Okay, and so they for many practical reasons, some of which we'll get into in the next chapter when we start talking about a bit more complex circuits. For a simple circuit, say just a light bulb and a battery, connections to the filament in the bulb are made along the tip and along the side of the cylinder. So you've got this insulator, right, in between these two metal pieces. And so your current would come in, say this bottom here, through the filament, and then back out through the side. And so this glass bulb, it's filled with inert gas. What does that mean? It means not oxygen, not something that's going to that is going to react with that metal, because when it gets hot, it's going to want to react. And so it turns out if you fill this with something that won't react with the metal, then it lasts longer. We'll often use this approximation of ideal wires, which turns out to be a great approximation. So, a light bulb might have a resistance of 3 ohms. This has a resistance of between 0 and 250,000 ohms, right? So, typically, the resistance of the components of your circuit, the resistors, the various things that you've put in there, are going to be much greater than the resistance of the wires. And so we can just ignore the wire. Ignore the resistance of the wire. So we use the ideal wire approximation quite a lot. In fact, from here on out, unless I've asked you about the resistance of wire or something, then if we're talking about circuits, we will be talking about ideal wires. So notice that an ideal wire, if it has 0 resistance, that means it's always at the same potential. Let's not forget Ohm's law, which we've written in this form here. But there's no reason why we couldn't rearrange it to look like this. And notice that in this form, it definitely says that if your wire has no resistance, then even with a huge current, there is no potential drop across it. So, in these ideal wires, we get no potential drop across them. So, if we were to analyze the potential of some simple circuit, presumably we've got some battery or something that's driving this current, then we would see that we'd have a high potential that would be constant. in the wire upstream from the resistor. As you move across the resistor, we get a voltage drop. Again, across the resistor, the resistance of the resistor is not zero, which means that if we drive a current through it, we will get a voltage drop across the resistor. Right? And so that's what's being represented schematically here in this diagram. No voltage drop across ideal wires. The voltage falls as I cross the resistor. Thinking about putting a battery in here, if I put this battery in here, then the battery gives potential energy to the charges. Those charges then move along the ideal wire at the same energy, right? So since the wire has no resistance, no energy is dissipated in this wire. And then those charges dissipate their energy. They deposit their energy into this light bulb. And so what we're really seeing is an energy transformation from electrical potential energy to light and heat. And remember that humans love to use energy. And we always use energy when we convert it from one form to another, right? We never use energy without converting it. And so that's exactly what's happening in an electrical circuit. We're converting electrical potential energy stored in the battery into something else that might be useful. In this case, we're converting it into light and heat. Again, looking at this schematic here, in the battery, the charges get some potential energy. They flow through the wire, and as they move through the resistor, they deposit their energy through collisions with the ion cores. When the electrons collide with the ion cores of that metal, they make them vibrate, and that vibration, of course, we can measure as increased temperature. So we say this a lot. We say how much energy, or what was the power dissipated by the resistor? What do we mean by dissipated? Well, really what we mean is converted from electrical potential energy into thermal energy. The rate at which that happens is given by this equation here. P equals IV equals I times, this is a little epsilon, and that stands for EMF. So we'll come back to that in just 1 second. Let's come back to that in just a second, and let's remind ourselves that power has units of joules per second, or watts, and electrical power is no different. So we end up with watts here, and that is simply current times potential, or potential difference. Now, what is EMF? What is E? This little epsilon stands for EMF. Now, in the previous chapter, I told you that potential voltage and EMF were all interchangeable. And essentially, they are. I think it's time now that we can distinguish between an EMF and a potential. So if I'm in a universe, and in this universe there's only one charge, and that charge will be represented by my half-eaten apple. My half-eaten apple here is my charge. This is the only charge in the entire universe. Is there potential in this universe? Yes, there is. However, this is not an EMF. An EMF stands for electromotive force, and an EMF is a potential that is caused by the separation of charges. The EMF is the thing that separates the charges. So I actually do need to have a positive and a negative in order to have an EMF, though with just one charge I can't have a potential. So looking back at the slide here, the battery is an EMF. Why is it an EMF? Because it physically moves charge. It physically moves charge from the negative terminal to the positive terminal. Therefore, we call it an EMF. It's a potential. It's a voltage. We kind of don't care, honestly. But you will see this symbol. You'll see this symbol, this epsilon, which is our EMF symbol. And typically we just say, hey, that is the EMF of the battery. So what is the EMF of a AAA battery? 1.5 volt. Most people would use the terminology, the voltage of the battery. And technically, we should say it's the EMF of the battery. But it's got units of volts, and for the sake of solving problems in this class, they're interchangeable. All right, so notice that we could substitute in Ohm's law here, and we could rewrite this I times V as I squared R, or delta V over R. Now, be careful. Any one of these three versions of this equation will work. It's just a question of applying it correctly. If we want to know the power dissipated by a certain resistor, that's what this notation means. This is the power dissipated by a resistor. This needs to be the current through that resistor times the voltage drop across that resistor. It needs to be the current through the resistor times the resistance of the resistor. The voltage drop across the resistor divided by the resistance. Be careful. It's be fairly straightforward in this chapter. In the next chapter, we're going to apply this to more complex circuits, in which case, you might have delta V's running all over the place, right? You might have 4 different values of delta V in your problem, and you need to be able to isolate which one we're talking about. So that's kind of the trickiest part here. Again, the equation itself is not tricky. It's applying it correctly that is. Let's just do a real quick proportional thinking example. A resistor is connected to a 3-volt battery. The power dissipated in the resistor is 1 watt. The battery is traded for a 6-volt battery. What is the power dissipated in the resistor now? Is it 1 watt, 2 watts, 3 watts, or 4 watts? Why don't you pause the computer, pause the video, and I'll see you on the other side. Okay, so we're going to want to look at this equation. And the trick here is to pick out the version of this that has one thing changing and the other thing staying the same. For example, if we were to look at this, I times V, well, we could look at this and say, okay, we had 1 watt dissipated, and then we doubled the voltage. So we might be inclined to say, hey, if we double the voltage, then we will double the power. What's wrong with that thinking? What's wrong with that thinking is that if we double the voltage, we also change I. So we can't just directly use this equation without a little bit more thinking, without another step in between. I don't think we want to use this version, although we could. It would just take a step of thinking in between. How about this one? We know the resistance doesn't change because it's the same resistor. Does the current change? Yeah, but without doing another step, we don't know how much. Let's not use that version. How about this one? Resistance stays the same. The voltage doubled. Oh, we're going to double the voltage, but it's under the squared, so we have 4 times the power, because 2 squared is 4. 4 times the power, we should have 4 watts, and indeed, PowerPoint agrees.